Afternoon, everyone. So you're very welcome to the application of heat pumps in commercial buildings. So we've got two very interesting presentations. First one is from Peter McMahon of EICL, and that's the application of heat pumps in buildings to decarbonise. So this will be mostly centred around retrofitting of heat pumps. So Peter has a huge amount of experience and worked on numerous projects. So obviously, electrification is a major important element of our plan to decarbonise, but heat pumps aren't a simple matter, and it's really important that they're applied in the correct manner. So Peter's going to bring us through some of the examples of that. And then after that, we're going to have Liam Kirwan from Daikin. So Liam, again, has a huge amount of experience on the heat pump area, but he's going to be concentrating today mostly on VRF systems, which again are a really interesting application. And they probably haven't been spoke about a huge lot, but they're a really interesting variation on heat pumps and are really good for buildings where retrofitting of, example, if you've got a building that's naturally ventilated with radiators and you need to install heating and cooling, VRF are a really good example of that. So Liam's going to talk about that as well as the new regulatory requirements around this technology. So Peter, I'm going to invite you to the stage and let you start off. Thank you.
Thank you, Eamon. Okay, so basically, heat pumps became much more utilised and integrated with building design, mainly due to the change in the building regulation. So Part L is really what spurred on the major change with regard to the integration of heat pumps. So I'm going to introduce you to some of the new technologies that have only been around in relatively recent years. I'll start with a little bit about what's happening, what spurred all this on, brief mention of climate change. We'll talk, like I said, about one of the types of the new multifunction heat pumps. The challenges that we have with regard to retrofitting buildings were immense. So manufacturers had to create new technology to satisfy these challenges that we had. So we'll then finalise talking about solar glazing, which is a brand new technology to this country, which we only launched a little over a year ago at the Architectural Exhibition and won an award. So we all know that there's a climate emergency. Years ago, we would have considered somebody that said that a tree-hugging hippie, but we're all clued in now, we're all aware of it, and it's a thing that we need to address. And very interesting statistics, just off the screen there. In a single hour, the amount of sun that hits the earth is enough to power the whole world for a year. So it's phenomenal. So even though the sun is somewhat creating climate change with the greenhouse effect, it also has the potential to satisfy a lot of the energy requirements that we have. So I don't know if any of you guys are architects, building engineers. Yeah, no? Yeah, good, at least one. So if you're an architect or a building engineer, nowadays we have a responsibility. We are the ones leading the change. Of course, we need to put pressure on governments. I saw Minister Eamon Ryan there earlier. Good to see people like that at events like this, because we have a responsibility. So I'm trying to do my bit, helping along. So very, very brief history. Historically, if you wanted heating and cooling in a building, you would have typically went for the likes of a VRF system. Liam is going to tell us a little bit more about VRF systems from Daikin afterwards. We much prefer water-based systems, and I know some of the VRF manufacturers are also creating a hybrid type system, but again, Liam will hopefully tell you a bit more about that. So the alternative to pumping refrigerant into buildings, which we are just totally against, it's not environmentally or we believe ethically the way to go. So the historical alternative was a water-based system. So you would typically have a chiller, a water chiller that provides the cooling, and you would have had a boiler that satisfied the heating. The problem with this, anybody that knows refrigeration and chillers will know that the condenser is basically dumping energy. So as we're cooling the water, we're taking energy from it and we're dumping that from the condenser to the environment. And at the exact same time, we could have a boiler running, generating heat. Okay, so you can see where the problem is here. That is the way it was done forever, and actually still is on certain projects you wouldn't believe. So the Museum Plaza, you'll have all seen on your TV every day during COVID. The Department of Health were giving their live broadcast from the building at the back there. And it's a good example of a typical building with a lot of glass surface where you will have a requirement for heating and cooling on a nice sunny winter's morning, like today, for example. On the north side, you wanted heating, and on the south side, you needed cooling. Okay, so there are situations where you need both at the same time, but to run a chiller and a boiler at the same time just made no sense. So you can see where we're going with this. Sorry, I'll come back to that later on, okay? So the obvious solution is multifunctional heat pumps. So these are basically like a chiller, like a heat pump. You have compressors, condensers, expansion valves, evaporators. We won't get too technical, but basically they're a little bit more intelligent. You have an extra heat exchanger to provide your heating, and like I said, very intelligent controls to give you what you want when you want it, okay? Now I'm going to go through the 3 modes of operation. It's a little bit technical, okay, but we're keeping it very, very simplistic. We have terminology, by the way, when we talk about efficiency. So if you're running at 100% input, 100% output, we call it energy efficiency ratio. So I'll give you an example. Let's say we have a cooling capacity of 300 kilowatts. Let's say we have a compressor absorb power. So basically the energy it takes to run that chiller will be 100 kilowatts. What you get out versus what you put in is the energy efficiency ratio, okay? Now, there are part load efficiencies and everything else. We're going to ignore all that. We're going to keep this very simplistic. So as you can see, in this first mode of operation, we are just cooling. Okay. So it's too far. I'm not going to try and reach and show you. Normally, I'd be able to do this, and the laser won't work either. So you can see heat exchanger number 1 is cooling only. So if we are in heating mode, we are simply diverting the refrigerant to the recuperator, which is basically the same as a condenser. So your refrigerant, high pressure, high temperature gas goes through the recuperator, heats your water, goes on through your refrigerant system, through your expansion valve. What was a condenser is now an evaporator. Again, apologies for anyone that's not refrigeration engineers or building engineers, but that's just the way the refrigeration system works. And we are heating. So let's say we now have 400 kilowatts of heating. Again, 100 kilowatts of input power. Again, I'm keeping this simplistic. The coefficient of performance is the exact same as your EER, what you get out versus what you put in. So our coefficient of performance is 4, okay? Now, this is the 3rd mode of operation where we're satisfying both heating and cooling at the exact same time. The external heat exchanger that was a condenser in cooling mode, an evaporator in heating mode, is now completely out of the equation. So you can see exchanger number 3 there is not being used. So again, let's say we have 300 kilowatts of cooling, 400 kilowatts of heating. We have 700 kilowatts of work being done. We still have the exact same input power. Now, some engineers will criticize me for saying that because design criteria comes into play, but again, we're keeping it simplistic. So now, again, you have a new term called TER, total efficiency ratio, but it's the same, what you get out versus what you put in. In this mode of operation, we have a TER of 7, more than double the energy efficiency ratio in cooling mode, okay? That is the main reason multifunctional heat pumps are now very, very common. We were introducing this technology quite a few years ago before the building regulations Part L came into play. And once the building regulations were changed, pretty much overnight, we had to try and eliminate fossil fuels, and the multifunctional heat pumps are now very much the norm in industry. So this is just an example of a selection sheet, a selection data sheet. We use our Airmec selection software from Airmec in Italy. It's Eurovent certified, so it does what it says in the tin, it's independently verified. So you can see the cooling capacity in this case is 500 kilowatts. The heating capacity is 640 odd kilowatts. The input power is 151. And as I said, the 2 of them combined divided by the input power gives your total efficiency ratio. So it's just to give you an example of a realistic selection that we've done. Very often when we're talking to consulting engineers when they're designing a new building, we want to know the heating load, the cooling load, so space heating, space cooling, and domestic hot water, the things that we need to satisfy with our heat pump technology. When we have this information, we can be, let's just say, a little bit more intelligent about how we select equipment. Historically, if you had 100 kilowatts, you'd select 110 kilowatts, what you want plus a bit, or maybe 2, half the size or something like that. we now know if we can maximize the total efficiency ratio, where we're heating and cooling at the same time, we are more than doubling our energy efficiency. So it makes absolute sense to get that information wherever we can and make very, let's say, more appropriate selections for the application. So we're very specific with regard to every application we satisfy. And of course, domestic hot water as well. So when the regulations changed, pretty much overnight, there was panic in the industry. A lot of these building engineers who had done it the same forever and a day, Eamon, I don't know if that's true, I think it is. So we had to basically re-educate people how to redesign their systems, allowing for this new technology that has to be integrated. So we basically created a designer training program. It's a 3-part, 1-hour series of presentations that we go out and we deliver to building engineers. And we basically explain how to design systems. Now, there were obvious challenges with regard to retrofit. A lot of the buildings pre-Part L were designed for heaters and, boilers and chillers. And consequently, the pipework, the flow rates, the temperatures, everything in the system was designed for temperatures that typically a heat pump couldn't deliver. So there was new technology, but there also had to be new design. So we had to basically look at the technology we're using, the design of how we implement it, and also the control strategy, which is extremely important. Okay, so that's what we do there. I'm literally going to give you 2 examples of schematics just to show you, like I said, an example of how you could achieve satisfying a retrofit application. So let's say where you have radiators that are sized for with the temperature from a boiler historically at 80 degrees C. But your client wants to decarbonize, they want to get rid of their boilers. How do they do it? With heat pump technology. Well, this is just a simple example. So we have here down the bottom left 2 multifunctional heat pumps that can satisfy your space heating and your space cooling. So as you can see, they're connected typically through buffer tanks, in this case as a decoupling tank, and then they're feeding a secondary water-to-water booster. That's another heat pump. Okay. What's very important to be aware of here is you need to allow the input power of your primary heat pump and the input power of your secondary heat pump, and you divide your total output by the 2 inputs, and that is the global efficiency of the system. You will not see that on any selection data sheet, because every selection data sheet refers to that piece of kit. So you need to do that calculation, or we can do that calculation for the engineers. However, having said that, if you have a multifunctional heat pump, as I explained earlier, they work in 3 modes of operation. And let's say it's the summertime, where the chiller would typically be dumping the heat from the condenser. We can recover that heat, so we're now getting a source for free. Okay, so that's an energy source that we can then use to give you a bit of preheat for your domestic hot water, or even to fully satisfy it. This is another example where we're satisfying, as well as the space heating, our domestic hot water. So you can see, again, multifunctional heat pumps up on the top left there, cooling up to the top, heating coming out of the bottom. And you can see we're connected to a couple of small water-to-water boosters. Now, the other thing to note here, if we're clever in our system design, if it's a new building, we can size the heat emitters for a lower temperature. So we don't need to size for 80 degrees the way boilers used to be sized before. If you put 80 degrees to a boiler, somebody's going to burn their hand on it, or to a radiator, I should say. So you don't need to do that. So we size typically a much lower temperature. We will oversize the heat emitters, and it will be more than adequate. Capital cost for the heat emitters goes up, but forever after you're saving with regard to your energy consumption. So that is a much more intelligent method of designing a system nowadays. There is a third an extremely efficient method of preheating your domestic hot water, pretty much 2/3 for free. ERMEC have done studies, extensive studies with the University of Padua, and they've discovered how we can utilize the free energy from a multifunctional heat pump when it's in chiller mode, and we can preheat our domestic hot water, typically about 2/3, and then we can use a water-to-water booster for the final third. I haven't put that schematic up because I can't show you everything here. So any building engineers that are there and you have a project you want to know, absolutely no problem, get on to me afterwards and I'll give you that schematic. So we are designing our systems intelligently. We're saving the planet. The polar bears have a chance again, but what else can we do? And there's always more that we can do. So like I said, new products, new system design, but also control methodology. So I'm literally going to tell you of 2 things that we can do to massively improve the efficiency of a system. About 5-6 years, I'm a refrigeration engineer by trade. I've come from the tools. I've worked on a lot of equipment that supposedly was good. And I've consistently found issues with regard to either design, equipment selection, installation, whatever it happens to be. So it's very easy to eliminate a lot of these problems if we're proactive. As an experiment, I went back to college about 5-6 years ago, pre-COVID. My last year was in the middle of when COVID had kicked in. And I really just wanted to learn what the building engineers are being taught, because I was teaching them about these new technologies, and I found a huge disparity in the industry. So I went to college, and I found a lot of the lectures are basically institutionalized. No disrespect, I know a lot of them quite well, and I've since become a guest lecturer myself. But technology has moved on, and it's moving on quicker than the lecturers can keep up and change their modules and get them approved and all this carry on. So hence the reason I go in and I give guest lectures. So very often we're brainwashed. Chiller, 6 and 12, 7 and 12, outlet, inlet. Heating, it was historically 80 degrees, 60 degrees, 20 degree delta T. We do not need to do that. If the load in a building has changed, or if it changes throughout the day, as it can, throughout the seasons, throughout the day, we don't need the same temperature all day or all year. We can have what's called a dynamic set point that simply reacts to the load at any given time. It's very, very simple. Okay, so that's the first component. Again, I'm not going to get into all selection data sheets, but basically you can see your efficiency will improve. The capacity of the chiller will also improve. It will increase as the ambient drops or as the set point increases. So there's huge benefits there just with regard to the efficiency of the chiller. Okay, so that's the first item. Very simple. Adjust the set point if it doesn't need to be as low as it does. Okay. The second thing I'm going to tell you about is very relevant to how compressors operate. So just to see if any of you are engineers, refrigeration or building engineers, I have 4 compressors here. Does anybody happen to know what these are? By the way, you have the answers on the left. You just don't know which is which. Okay, so the first one, number 1. Anybody? I know when you have peers all around you, nobody ever wants to speak up. Okay, so number 1 is the non-inverter screw compressor. Okay. Number 2 is the scroll, Copeland scroll, the most common type of compressor in chillers nowadays and heat pumps. Number 3 is the inverter screw compressor, and number 4 is the turbo core. There are reasons why I'm telling you about this, okay? So every chiller has a different performance curve dependent upon the type of compressor, the efficiency, there's all sorts of factors to come into play. They will all have a performance curve. This is just an example of some of the performance curves at different ambience for the scroll type chiller. So you will see at 100% load, which on the bottom here, let's just say we use a design ambient in Ireland, by the way, around 27, 28 degrees C. We're selecting a chiller. So around the middle row there, you'll see the green line is for 27, and you can see the efficiency increases. By the way, over on the left is your energy efficiency ratio. So you can see as the load drops off, the efficiency increases, okay? You'll get the gist of why I'm saying this now in a minute. The screw compressor, again, you can see it increases, goes up, kind of peaks, drops off. The non-inverter screw is better again, consistently improving as the load drops off. And the turbo core by far has the best part load efficiency. By the way, it is also, of course, the most expensive and very, very specialist. But there's one common thing I hope you've all picked up on. They are all at their least efficient when they run to 100% load. Now, if you go back to when I was on the tools, I commissioned so many chillers over the years, and the intelligence of how they were controlled, you typically have a BMS system and you had 4 wires going to every chiller, 2 to enable and 2 for alarm. So one chiller you would run up to 100%. If it didn't satisfy the load, you would then bring on the chiller, the second chiller. There was no consideration for the efficiency of every single chiller. So we now know running them to 100% does not make any sense. And I even had some conversations with my lecturers about this. So the manufacturers obviously realize this, and they've developed their own software because the performance curve is going to change for every type of chiller and every type of heat pump. So they have what's called a multi-chiller sequence controller. This is the second thing I'm just telling you about that you can do to massively improve the efficiency of a system. So that simply communicates with every chiller. It monitors, I'll just move on here. You can see it's connected. You have a temperature probe on the common outlet and common return. There's a direct correlation between your load, your delta T in temperature, and how it manages the efficiency of the chillers. So let's say chiller number 1 is getting up to 70% load. It says, right, if I keep loading up, I'm going to be very inefficient. I'm now going to bring on chiller number 2. I'm going to run 2 of them at lower load and at a much greater efficiency. Every system where we have 2 or more chillers now, we offer this, and it is always being adopted and implemented. We introduced this to the market probably about 5 years ago, and like I said, it's now pretty much common. So again, just 2 of the items I wanted to tell you about. Now, we're all here at the Energy Show. No matter how good we are with what we do with regard to reducing energy consumption in HVAC systems, they are always going to generate energy. So you'll see there's a lot of stands around here with solar power. Now, again, I've been on the rooftops. I've seen where we have our chillers, our heat pumps, our air handling units and everything else. There very often isn't space on the top of buildings in the likes of Dublin city centre to have solar panels. It's a major challenge, okay? Now, you walk down, let's say the quays in Dublin there, look at all the buildings, look at all the glazing on them. We can now use the glazing on buildings to generate electricity. There is such a thing as photovoltaic glass, okay? This is in the industry, well, in the market for probably about 9-10 years at this stage. We introduced it to the Irish market about a year ago. I was away on holidays. I don't tend to relax very much on holidays. So I was on the internet and I discovered PV glass. And to me, it was just like a bolt hit me. I just thought, this is an absolute no-brainer. So now, if we can generate energy from the glazing on buildings as well as reducing the energy from our HVAC systems, we are now starting to get closer to that carbon neutral. Now, because it's PV glazing and we have the architectural vision of what they want on a building, there's a trade-off between the power you generate with PV glass and the light transparency. Now, there's different types of technologies. You have crystalline, you have amorphous, you have organic PV. There's various types with different power transmission or power generation and different light transmission, okay? So, like I said, we can now use the surface of the building. You know, you could have your glass where you need your vision pretty clear, which won't generate much power. You might get about 40 watts per meter squared, but you can use your spandrels. A lot of the buildings you'll see with solar shading, that is to reduce the load for the air conditioning. Because unlike years ago where we had a huge, sorry, how am I doing for time? I'm on 20 minutes because I know Liam is waiting there. So years ago where we had to have solar shading to reduce the air conditioning, we can now use the PV glass to reduce the solar heat gain and also generate power. So this we've been promoting for about a year. I only discovered last week there's going to be a new building regulation comes into play, the Energy Performance of Building Directive. I always get it wrong, don't I? Thanks, Eamon. I have to look at Eamon. But I'm told by 2026, every new commercial building has to have solar power. And by 2028, every building will have to have solar power. So just like with the Part L in January 2019, when that came into play, multifunctional heat pump took off. The photovoltaic glass is going to take off from 2026. We are already getting a lot of inquiries, and we think, you know, for anyone that's ahead of the curve as we are here, they'll be getting on board, and that's what we're going to see. That's the future. Okay. I've been interviewed, by the way, by loads of radio stations at the tech room. If you want to go onto our website, clearenergy.ie, there's an interview I've given there. You can integrate PV glazing, curtain walls, facades, skylights, canopy, all sorts of applications. So just to finish off, some of the projects we work on, you will all know, Hanging Gardens in Limerick, Dublin Airport, of course, you all know about, the EXO building just across the Liffey there, and Salesforce, which is one of the most, we actually won the most innovative project award for that. So point is, proof is in the pudding. So that's it. We have a team of engineers. We are dedicated to helping consulting engineers and architects. So if anybody wants our help, you know where we are. So I don't know if you want to go questions now or wait till after Liam. Okay. So if you have questions, I'll hang on, and don't be afraid to come up to me afterwards.
Thanks a lot, Peter. That was great. Obviously, there might be a bit of disagreement in regard to the whole VRF and its ability to be used in buildings, but certainly it's horses for courses, and I know there's a lot of retrofit buildings out there where the installation and the pipework requirements, I suppose, in terms of multifunction chillers aren't practical. So I still think VRV or VRF is a good system. But anyway, you can have a round the car park about it later. But so just coming up next now, as I said, Liam from Daikin is going to go through the whole side of the VRF, or it's VRV actually is what Daikin call it, because they painted it that name to protect the technology. And then everyone else just started calling it VRF, so it wasn't really a particularly successful mission on their part. But anyway, so it's a really good technology. I suppose that, as I say, it hasn't been spoken about that much in terms of the whole retrofit side of things, but it really does have its place. And Liam's going to be talking about the use of R32, which is a much lower global warming potential than some of the other systems, some of the other refrigerants being used out there. So over to you, Liam.
Hi folks, Eamon, thank you very much. Just as we say VRV, as Peter mentioned, VRF, the difference between VRV and VRF is the name VRV is patented by Daikin globally. So VRV means variable refrigerant volume, where other manufacturers use it called VRF, it's variable refrigerant flow. But the name VRV is patented to Daikin, that's why at the moment we're the only ones that use the name VRV. So my presentation today is to look at why the commercial sector of VRV or VRF is changing away from refrigerants with higher GWP refrigerants. So over the next, I suppose, few months, next couple of years, you're going to notice that the VRV market is going to move towards water and R32. So as we said, I'm going to talk today about why VRV is moving and why the industry is changing to R32. So if we look at the agenda for today, I'm going to talk about the HFC phase downs, on why we have to move to a lower GWP refrigerant. We're going to look at the move to R32, so how the industry as a whole is going to move towards R32. We're going to go through the legislation. So because we have a new refrigerant, we have a new legislation set out by Europe. So as manufacturers, installers, suppliers, whatever it is, we all have to abide by these legislations for safety, for safety. And then I'm going to summarize, and then again, if there's any questions there for myself or Peter, we'd be glad to answer the questions. So if we look at the HFC phase down, so what we can see from this chart is the phase down of HFC up to the year 2030. So what we can see is that the tons of CO2 equivalent by 2030, they want to bring that down to only 21%. So how do we do this? We do this by, number one, using higher efficiency machines, by moving to inverter compressors, by using the efficiency fans, by using better PCBs, and also by changing refrigerant. So what we can see here in the light blue, is there a laser on this? So in the light blue, I don't know if the laser works, we can see that R410A is probably the most popular gas in the VRV or VRF market. We call it the air conditioner market. So 410A has been the most popular gas over the past many years. Now that we have to start moving towards lower GWP refrigerants, which is global warm potential, you can see by 2030 up to 2033, the orange section of R32, there'll be a greater use of R32 where 410A then will start to slowly but surely move away as the industry standard gas for our industry. So how do we do this? How do we do this phase down? So we have to look at refrigerant phase out. So the plan is to reduce any refrigerants above a GWP of 2,500 by the year 2030, I think it is, which means any gas that has a GWP higher than 2,500 will be banned. So the industry needs to move to lower GWP refrigerants. We then have to look at the refrigerant phase out. So as I said, refrigerants that are over 2,500 will be banned. We want to push towards lower GWP refrigerants. So all manufacturers, whether it be Daikin or Airmec or any manufacturer, will all be looking to use better refrigerants, more efficient and lower GWP. There will also become a ban on domestic air conditioning splits. So in the domestic market, we don't really have a major air conditioning domestic market here in Ireland, but across the continent, across Europe, where there's a very, very large domestic market, they would look to ban any system using 410A to have more than 3 kilos or more. So again, they want to push towards R32 because R32 uses less refrigerant compared to 410A. So the ban will come in that any split system in new builds or new installations, they will not be allowed to have more than 3 kilos in the domestic market. And then we look at new measures of the environmental impact. So what we have taken into consideration is that if we have a system with gas, any kind of gas, if the potential of a leak happens, so if we have a system with 410A, 134A, or 32, whatever the gas may be, if that system has a potential leak, we have to look at the tons of CO2 equivalent that system will expose into the atmosphere if it leaks. So again, we have to reduce that amount of tons of CO2 equivalent when we look at R32. We then have to use less leak checking. So if we have less refrigerant in the system, it means we don't have to be checking the system for leak checking as much as if we have larger amounts. So it means that if we don't have to touch the system by putting gauges on it or checking it with other bits of materials, there's less chance of a leak. So if it's sealed system and it has less refrigerant, it means you have to do less refrigerant checks in it. So we eliminate the chance of losing refrigerant during maintenance. And then the last thing is the different properties. So we have to be sure that when we use the refrigerants, we have to ensure of what refrigerant they're using. We have to find out the safety aspects of the refrigerant, whether, as I said, it's R32 or HFOs. It's very, very important on the safety aspect that the engineers, the manufacturers, the people on the system know the gas they're working on and know how to handle it and know how to use it safely, because safety is a big factor in our industry. So as we said about the HFC phase down, the F-gas phase down we call it, these are the major gas that we use in our industry. So from 404 to 410 to 134 to R32. As you can see, there the line there is by 2030, the ban of anything over 2,500. Now there is talks that larger countries across Europe are trying to bring this ban down even lower. So it could be a fact that in 5 years, 3 years, whatever, it could be even before 2030, when we're told by the larger EU states that this refrigerant will drop down, there's talk of the VRV markets dropping down to 700 GWP, which means 410A will also be then gone off the cards. But at the moment, the benchmark is 2030. So how do we move to R32? Well, there's four main aspects like any refrigerant or anything we work on. We have to look at safety. It's very, very important that people working on R32 or any kind of refrigerant, they know the safety aspect. So it's very important that people are trained. So Daikin, like all manufacturers, give constant training to our engineers, our staff, our service partners on how to handle the refrigerant in the most safest possible way. There's also the environmental impact. As a global leader in air conditioning manufacturing, we have to be sure that the products that we are producing, whether it's for heat pumps, whether it's for air conditioning, whether it's for chillers, we use the most environmental friendly gases in the world. We then have energy efficiency. Now, energy efficiency is a great thing we can talk about. Oh, we use the best gas. And it's all well and good, a company like Daikin investing into R32. But we also have to look at the running cost of the machine over the lifetime of the system. So we have to ensure that the compressor is fully inverter. The PCBs are correct. The expansion valves are correct. The fans on the indoor unit is correct. There's no point in us launching an R32 system, but then the compressor is very bad. So the whole efficiency of the system, from the gas to the running cost, the amount of electricity the system is using is critical. And then we looked at the cost effectiveness. As we said, if we design the system, whether it be a VRV or a split system or a SkyAir system, if we design the system, we have to ensure that the end user, whether it be a commercial building or a residential building, is that the system is cost effective and the lifetime of the system, the end user is not paying through the nose on the electricity cost. Because as we all know, with the cost of living going up, it's very, very important that we save on electricity. So we need to ensure that these are the most high efficient system in the market. If we then move to R32, so this was a multi-year study. It was carried out by the US National Institute of Standards and Technologies in America. And they looked for many years of the best replacement for 410A in the air conditioning market. And out of all the chemicals, they tested more than 60 million different fluids in America. And out of those 60 million fluids they tested, they only came up that 27 were suitable for replacement of 410A moving forward in the air conditioning market. Now, out of this study, they have basically stated that it's very, very highly unlikely that better performing fluids will be found than R32. And that's why you'll notice now that all the large Japanese manufacturers and other manufacturers around the world are going to start shifting to R32 over the next few years. A lot of them have already done it, but a lot of them will follow suit and then move to R32. So, performance data in today's system. So what I've done is I've taken just the typical gases we use in the industry. So here we have the capacity against the efficiency. So if we look at R410A, now 410A to me is a brilliant gas. As an engineer, I'm an engineer myself. I came through the tool, so I know the 410A. I know it's a very good gas. But as you can see, it's one-on-one. Its efficiency is one, its capacity is one. So it's just a standard gas. Then we look at R290, which is propane. Again, higher efficiencies, but lower capacities. So it's ideal for different markets, like heat pumps. It's a great gas for heat pumps. But for air conditioning, not so great. Then we look at the 1, 2, 3 gases, okay? Again, different kind of gas compared to the VRV market, but just as a sample, lower capacities, lower efficiencies. But again, these gases are ideal for certain industries in our industry. And then we look at R32. So R32, as you can see, has the highest efficiencies and the highest capacities compared to any other gas on the chart. So when we look at the measurements of the tons of CO2 equivalent, as I said earlier on, a sealed system has potential of leaking. No one in the world can say, oh, my system will never leak. Moving parts move, things happen, accidents happen. There is the potential, we have to look at the worst case scenario, that there is the potential of refrigerant leaking out of the system. So we have to look at the tons of CO2 equivalent. So what I've taken here is R32 against R14A. So what we know is R14A has a GWP of 2088, and we've charged their system with 10 kilos of refrigerant. If those 10 kilos were to leak out into the atmosphere right now today, that would be the equivalent of 20.9 tons CO2 equivalent into the atmosphere. If we take the system right beside it, R32, GWP is 675, charged with the same 10 kilos, the same weight, and it leaks out, it's only 6.8 tons of CO2 equivalent. So it's a massive difference, okay? That's why the choice to move to R32 in our industry is the chosen one. So if we take these two systems, well, here's two typical split systems. And on the left, we have an R14A split system. And in that system is 1 kilowatt gas. And let's say, for an example, that 1 kilowatt gas is delivering 1 kilowatt of energy. Okay, let's call it 1 kilowatt coolant. Our GWP is 2088. Okay, so we know if it leaks out, it's going to cause a higher tons of CO2. The same system next door to it will also deliver 1 kilowatt, but it only has 0.7 kilos of refrigerant. So with R32, we use less refrigerant, but we get higher efficiencies. And again, the CO2 ton equivalent is completely down compared to 410. So how do we work out the GWP and the higher volumetric efficiencies? So what we look at the GWP values. So as you can see, the GWP of R32 is only 32% compared to 410A. The refrigerant charge, he said, is 30% less. When we multiply one by the other, we get up to 22% efficiency. Sorry, I'll come back here. There we go. So as you can see here, the CO2 ton equivalent is massively dropped between 410A and R32. So not only is R32 a better efficient refrigerant, it's also a better refrigerant for the industry. If we then look at what's called our seasonal data, so seasonal COP and seasonal EERs, we've taken the two systems, and these are like for like, an 8 to a 20 horsepower VRV system. You can see in blue is R410A, and the exact same system, same horsepower in red is R32. So what you can see is from the same data taken from the two same systems, same applications in typical office block, I think this was, we took the same data, we recorded it over a same amount of time. You can see that up to 14% increase on the seasonal data and up to 8% increase on the average of the SEER and the SCOP, which is based over the heating and cooling of the system running in the same conditions. So you can see that R32 has a much more efficient gas than R410A. So why going with the Daikin VRV5? And I'll explain what we can do with this and why we have to go to R2, we have to move on through the legislations. With the VRV5, because it's there to decarbonize the commercial industries, when you select VRV5 and your project goes with R32, you can automatically apply for an additional credit when it comes to LEED or BREEAM because of what's built into the system, because of what delivers back, and because of such high seasonal efficiencies compared to 410A. Now, when we talk about the move to R32, especially people that are on the tools, engineers, architects, consultants, and designers, what's the big difference? Okay, is it like CO2, where CO2 runs at very, very high pressures? Okay, R32 is virtually the same as R410A, and I'll explain why. As we can see here, every engineer that's worked on 410A over the past 20 years, 50% of R410A is made up of R32. So they've all worked on R32, they just didn't know about it. Because it's a new A2L category, it's specifically designed for a safety standard of R32, okay? So because it's a new category of refrigerant A2L, we have to look at the safety factors. The installation is virtually the same as R410A. The only difference on the VRV compared to 410A is your liquid line and your suction line are a lot smaller than would be a 410A. So the overall cost of the project is going to come down because you don't need the same bore size copper to move the refrigerant around. So it's a very, very good gas. Also, R32 is a single component refrigerant, okay? So it condenses and evaporates at much better temperatures, where R410A is made up of 2 components. R32 is a single component refrigerant, so it's a lot easier to use. So if we look at the legislation and if we look at why we're moving to R32, we didn't just wake up one day in Japan and decide we're going to go to R32. Obviously, as manufacturers, as installers, as contractors, we're now being forced to move with the times and bring out more efficient systems. So if we look at R32, we have to look at the safety aspects and the different classifications of refrigerants. So if we look at toxicity, toxicity is measured with capital letters A or B. So depending on how toxic the gas is or the chemical is, it's an A category or B category. As part of that then, that comes under a generic standard. That generic standard is called EN 378. And that's what we use to design air conditioning, especially for the likes of hotels or hospitals or prisons where people are sleeping in occupied spaces. We have to look at EN 378 because of toxicity. So we need to ensure that if refrigerant leaks into the building, is there enough refrigerant in it to be toxic to actually harm someone, or is it safe? If it's not safe, you have to put in leak detection. If it's safe, well, then you can get away with leak detection. Now that we move towards a more flammable refrigerant, we now have a new standard, and that's identified by letters 1, 2, 2L, and 3. So now that's where we get the A2L refrigerant, okay? So as we can see now, this is now called a product standard. So with a product standard, it will prevail EN 378, and I'll explain as we go on a bit more. So why do we apply these standards? We apply these standards because R32 has been classed as an A2L refrigerant. It is very slightly flammable, but has been deemed one of the safest and best gases in our industry. Now, don't let the word slightly flammable scare you. As you can see, an A2L burns at a velocity of less than 10 centimeters a second, so it's a very, very safe gas. It has to have a constant flame for it to ignite, and once the flame disappears, the refrigerant stops burning. So it has been classed across Europe and across the world as probably the best refrigerant for this industry that we're all part of. So, why do we apply these standards? Well, EN 378, as we said, is a generic standard, and it covers the toxicity and the flammability, okay? But R410A is not really flammable. So when we look at 410A compared to 32, we're just looking at the toxicity. When we look at R32, the IEC 60335 covers the flammability. But then you ask, well, if EN 378 covers both flammability and toxicity, why do we have a new product standard? This product standard only covers the flammability of the refrigerant. So if we have a case where we have R32, we have to use the product standard, the IEC 60335-2-4, because it's a product standard and not a generic standard, and it prevails EN 378. So it's very, very important that we don't get confused. If we're doing a project with R32, again, as manufacturing Daikin, we'll do all the design work, we'll do all the calculations, and we will tell you if your system complies with the IEC 60335. So as we said, product standard, it prevails in EN 378. So to summarize, the applicable legislation regarding the refrigerant safety groups, i.e. the IE 60335, and takes preference over the one for the product standards, okay? So, so we have to abide by IEC. The EN 378 being generic standard, sorry, I can't read that, is a relevant legislation for the points covered by the IEC. So if we are unsure of something and it's not in the IEC, we can always refer back to the EN 378. But when we're using R32 in a commercial application, it's very, very important that whether you're an architect, a supplier, a contractor, a manufacturer, that you make sure you're in compliance with IEC 60335, because as we said, it is a product standard, it's a European standard, and it's very, very important that we apply by this. So how do we apply by this? So what they've laid out is that in certain scenarios, when we use R32, so for a hotel, a hospital, a small office where there is the potential of R32 leaking, they've brought up 3 possible countermeasures that will allow us to use R32. So what they've said is, you must have an alarm in certain applications. Now that alarm must be audible and visual. And that means that if someone is in a hotel and they're asleep, the alarm will not only flash, it will also be very audible. So they'll hear the alarm, you know, and like me on a Saturday night, they'll probably pass down the hotel bedroom after being out a few beers. I need to hear the alarm going off. I see a lot of people smiling, so I know you're exactly like me. So the alarm has to be both audible and visual. It's very, very important. We then have shut-off valves. So when something leaks into the building, it is crucial that we isolate our refrigerant leaking into the building, okay? So you have to be able to isolate the refrigerant going into the building. If you isolate the refrigerant going into the building, it means it's not a massive safety issue. And then there's also ventilation. You can have mechanical or natural ventilation. And what that means is that if the refrigerant leaks in, the refrigerant then will be removed from the building, making it very, very safe. So what have Daikin done? So this is just a literally 2-minute video, and this just is going to show you, and you'll probably understand that we actually won the highly commended award for this VRV5 here today at the Energy Show. So thank you very much, guys. But this video will show you exactly what the standards are and exactly what Daikin as a global manufacturer are doing to protect you guys as installers or architects. We are taking responsibility for these safety measures. We're not going back to you guys and saying, put in R32 and then bring in a third-party contractor to put in leak detection, to put in isolation valves, to put in alarms. Because if something's to happen in 6 weeks, 6 months, whatever, who's responsible? Is it the third-party guy that put the alarm in? Is the third-party guy that put the leak detection in? No. Daikin have included all the safety measures for R32 in the new VRV5. We have a stand here today, E5. If you want to come over and see more of this, we'll be there all day. But I'll just push this very, very quickly on. Have you got sound?
Shirudo technology work. In the unlikely event of a refrigerant leak, the integrated sensors in the indoor unit will immediately detect it. The leak detection sensor then activates a local audible and visual alarm integrated in the Madoka controller. Via a field setting, the Madoka controller can be set to alarm only. If a supervisor alarm is required, it can easily be integrated via the Madoka controller, or as a third-party alarm via an output of the outdoor unit, via the indoor unit, or through the Intelligent Touch Manager. At the same time, the refrigerant control measures are activated, closing the shut-off valves of the specific branch, minimizing the refrigerant that can leak, and maintaining full operation for the rest of the system.
That was just a very quick example of what we're doing. As we said, the whole goal, we are moving to R32. The industry is going to move to R32. So it's very, very important that when we use R32 as a refrigerant in any application, we're covered by this IE 60335. So to summarize very, very quickly, we all have to reduce our global warming. And the main impact of the air conditioning heat pumps is the electricity we use. I know a lot of people here have heat pumps in the house. They could have air conditioning in the house. They could have air conditioning in the office. It's very, very important that we're conscious exactly that unit that's doing the heating or the cooling in the building, is it efficient? Why is my electricity bills through the roof? Have I got the best compressor? Have I got the best refrigerant? Have I got the best unit? So it's very, very important. We then recommend models start using top class efficiency. So we always look for A++, A++. So always recommend that when you're buying a unit, it is the highest efficiency you're looking at. The other impact from refrigerant gas in the system. So as I just said here, we're moving to R32. I know our colleagues in the heat pumps department and a lot of people here from the heat pump people are moving to R290. So it's all about moving towards the best refrigerant for the application. And then lastly, we recommend using models with lower tons of CO2 equivalent like R32. And then consider the total equivalent warning impact on the system. So any questions? And thank you very much for your time. Are you okay? Any questions?
Thanks very much, Liam. That was really interesting. It was a really impressive presentation, even though you had to use the word flammable, which is really impressive. And that video, I think that was the presenter from the X Factor that had the voiceover and that, so it sounded really cool altogether. So I don't know, has anyone got any questions for the guys? Yeah. Just one sec, she'll give you that.
Hi, thanks for that. That was great. So my name is Nathan. I work at Indeed.com. So we've got a 7-story building down in Capdock, and we have F-gas that we use. And we're looking at how can we swap out our F-gas to R32? Is there anyone providing that service in Ireland at the moment, or?
Yeah, you can change, but the difference is with R32, because it's a single glide refrigerant. If you just take out the I don't know whether you have Fortinet or what you have in the system at the moment, but if you just remove the gas out of the system and put in R32, you could have issues with with capacity, efficiencies, temperatures, oil, and everything. Because R32, most manufacturers now have gone to R32, they have brand new compressors, they have brand new expansion valves, they have a new oil management system. So if you're looking to say, I want to change my air conditioning unit to R32, you would have to change the indoors and the outdoors. Yeah.
Okay, thanks.
No worries.
Anyone else? No? Must have been very impressive. Yeah, so if you want to talk to the lads, E5, stand on E5, and Peter's taking a novel idea, taking over the stage instead, so you can just come and meet Peter at the stage if you want. Okay, thanks everyone.